Hi students, welcome to HSC Chemistry with a bit of a twist today. Over the last probably couple of weeks, a few questions have started to roll in, just looking at some of the specifics of the course, some of the little details that are worth looking at. And so I thought what I'd do just to help you all out is just to put these different questions that I've been getting on videos. Hopefully you'll find some of them useful. And if you already know the answers, well, then you can just scroll straight through. These are all questions that I've been asked. I've answered them, and usually I send email responses straight away. Oh, or not necessarily straight away, but as soon as I can. But I only send them to the person who asked the question. And I thought probably the questions that are being asked are so good that more people might benefit from the answers. So let's have a look at a few. Why do we add barium nitrate slowly rather than quickly during the sulfate experiment? One of the problems that we have when we are forming barium sulfate is that the barium sulfate itself, the barium sulfate precipitate, is very fine. It's a very fine precipitate. Okay, it's almost powder-like. And the point around controlling the rate at which we add the source of the barium ions, which could be barium chloride or barium nitrate. Oops, try that again. In order to have that source of barium ions, if we add it very quickly, if we just throw the two together like we have for some of our precipitation reactions, precipitate forms very, very quickly. The particles are very, very fine. And we already have a problem with the filtration in this particular experiment. It's very hard, certainly with our normal filtration methods, to be able to gather these very fine particles of barium sulfate. So that's why we use things like sintered glass, funnels, and slightly more controlled methods in order to make sure that we really are trying to allow these particles to clump together, to agglutinate, or possibly even to form a flocculate. Okay, in the same sort of way that we talk about it during the process of water quality treatment. So we're trying to get these tiny little particles which just form randomly everywhere to try and form, I guess, in a more controlled way so that they stay fairly close to one another and start to clump. This just means that they become easier to separate when we go through the filtration process. If it's nitrates, phosphates, and sulfates that provide plants with nutrients, why do we have to attach it to ammonia and not to a group 1 or 2 element? One of the big problems with soils is that they are very poor in nitrogen and phosphorus. Australian soils are particularly bad at these two very important elements, even though they are often found in just trace amounts. So we call them trace elements. But they are critical for plant growth, and therefore the plants need nitrogen and phosphorus and plenty of other things as well. And the way that we get these into the plants is through things like nitrates or phosphates. You see, the problem is that around 78% of the atmosphere is nitrogen gas. And you would think this is fantastic. This is heaps of nitrogen, no problem with plants needing nitrogen. But they can't use it in this form. It needs to be fixed. The nitrogen needs to be fixed in a form that can be absorbed by the plant. So the easiest thing for us to do is then fix it to an ion like a nitrate, where we know that nitrates are soluble, so it will dissolve in water, and therefore it can be absorbed through the plant's roots. Now, for fairly obvious reasons, ammonium, is an ion as well, and it's also an ion that is rich in nitrogen. So having these two in combination, ammonium nitrate, or a very common fertilizer is ammonium sulfate, sometimes called sulfate of ammonia for obvious reasons, is giving you a source of both the nitrogen and, in this case, the sulfur at the same time. So this is a nice little double dose of nitrogen. It allows nitrogen to be in the to be able to be taken into the plant through its roots in the soil, and as a consequence of that, is able to have a much higher hit of nitrogen. Of course, nitrogen is one of these very important components of amino acids, which link together through polymerization to form proteins. So there's no reason why we couldn't have a sodium sulfate or a potassium sulfate, but the reason that we use the ammonia is it just gives us that extra hit of nitrogen. What are the most important features of the saponification reaction? Okay, so this is specifically designed to target those who are doing the industrial chem option. Saponification is the reaction between a fat or an oil and a base. And what we get is a soap and water and an alcohol. Oops, alcohol. Soap and an alcohol. Now, the most common types of fats and oils are those that have the glycerol backbone. Okay, so effectively, the glycerol is going to have 3 OH groups, and it's from these OH groups that we're going to form our ester bond. And this is one of the reasons when you're comparing the process of industrial saponification to that in the laboratory, this is one of the ones that this one can be one of the differences, is that you can just use an ester, which effectively is, as we know, this kind of a thing. And so what we're doing is we're going to break the bond anywhere you like, really, but between these, so either here or here. I'll put a different color there. And what we're going to do is find that the alcohol groups re-establish themselves, and also that what we have left on the other side is our organic acid ion. So these are all anions, they're alkanoate ions, excuse me, and the soap is just whatever our cation is linked in there. Do be aware and don't fall for the trap. We could just as easily put potassium hydroxide into our solution, and the only thing that changes is that the soap is now a potassium soap rather than a sodium soap. So this is just an important step to be aware of here. The glycerol, which I didn't sort of quite finish drawing here, and obviously you're going to be getting sick of writing hydrogens everywhere, which you will do, and this is going to be some length of carbon chain across here. These are, of course, our components of our soap with the cation. I'll just put cat at the front, depending on which one that is, sodium or potassium. This is some of the key processes that are part of the saponification reaction. Now, again, it's a slow process. You need a controlled heat in order to do this. You also need to salt out those particles as well, because we want to try and add in, what we often do is add in something like sodium chloride, add a lot of additional ions in there to make sure that we precipitate or push out our soap from the solution, leave the alcohol in the solution. So saponification is one of these important reactions that involves the addition of a fat or an oil or sometimes an ester to the sodium hydroxide in order to form the soap and the alcohol group that's left. So just think about this as a reversal of an esterification process, but instead of having a water group here, which is what we have when we form the acid, instead we have a sodium hydroxide or a hydroxide here, which is still going to get us to form that alcohol group, but we're actually going to form a salt instead of the acid. Hopefully this helps. If you've got any more questions, just email them through, and thanks for watching.